Okay, hi everyone. It is week 7. That means we are almost done. Or at least we're past the halfway mark. I can only imagine how absolutely burnt out you're all feeling. So this is a relatively low-key lecture. I am going to introduce one thing that is going to blow your mind a little bit and kind of make you wonder why we're doing all the rest of the course. But what we really want to get to over the next few weeks is making sure we have members with the correct capacity. Remember, the first half of this course was what are the loads on it? And in fact, what are the factored loads? And what are the combination of all those factored loads? And not just the loads acting on the building, but then the internal loads in every element, whether it's the columns or the beams, or like for the shear and the moment, or a truss with axial loads as well. So we needed to be able to figure all of those out. And now what we need to do is say what the capacity of the material is, or the member that we want to use to support those loads. But here's the thing, you guys don't know anything about material science. A lot of you don't even know what basic construction looks like. And what I've discovered is that there's no one else in the program that really shows you that, because a lot of it is so interpretive based or creative based, because you guys move right on to extremes. You know, there's barely this opportunity to look at the norm before you're going on into what is wild and crazy, which is awesome. I think our school needs that, because that's why we're kind of a design-based university for architecture. That means, though, that you need me to show you what basic construction looks like. So the first half of this lecture is me introducing. We're going to start with steel. So I'm going to introduce steel construction. Why do we do it? What members are available? What does it look like? Then I'm going to move on to steel sizing guidelines. Now, guidelines, or some people might call them rules of thumb, are what you would do in very preliminary designs. So this is not engineering. This is simply what people have done again and again and again and again, and they know it's pretty darn close to right when things are kind of boring and normal. So this isn't pushing the envelope kind of stuff, but it is what you would put on a preliminary set of drawings. And then the last half of this lecture is honestly a bit of a snooze fest, but it's good because it's showing you images of basic steel construction. You now kind of have a little resource that you can go back and be like, what does that weird thing Shannon talked about look like? Even if it's, 10 years from now, maybe you can go back to some of these images and just see quickly kind of this collection of what these construction types look like. Next week, we'll actually look at the deep science behind steel and talking about if we can calculate that a member works. Does our member have enough shear capacity? Does our member have enough axial capacity? And does our member have enough bending or moment capacity in the particular member we're picking? So let's move on to basic steel. Okay, so just some kind of terminology. It's early morning, it's like 4 in the morning, and so it's hot and then cold because the heat is coming on and off after having been off all night. So bear with me a little bit. You'll see me taking my sweater on and off. And also, Dave isn't here today. He had to stay downtown in Toronto. Actually, that means nothing to you guys, which means I have the kids here by myself, which means when they wake up, you're going to see a weird jump in this video. Because they will wake up. They know I'm trying to record. Well, they don't know, but inevitably they'll wake up because I'm trying to record this lecture. Okay. So some terms and things you should know about steel and how it's created and what it looks like. So, hot rolled steel. Now, all steel is, I'm assuming you know the basics of where steel comes from. Not necessarily structural steel, but basic steel. They take different elements and melt them down in a forge and mix it up as a big liquid. And there are chemists there testing it. As much as it's a big messy shop, it is a very, very refined process. After this steel has cooled down, we now need to turn it into the shapes we need to. So the way we turn it into the shapes we need to is we have two different ways we can do it. The first one is hot rolled. So most large or complex shapes are hot rolled. So what they do is they take these long squares of steel and heat them up back to red hot. They're not melted, but they're just short of melting. So they're very, very, very hot. And if you've ever worked with bread dough, or for example, I have done a lot of baking over the past 2 years. I hate baking, but I've done a lot of it. But my passion is bread, obviously, because, you know, I'm a mom during the pandemic. So I made sourdough. If the dough is cold, you can't do much with it. But if you warm it up, it gets really plastic almost. So what we do is we heat up the steel to red hot and then push it through rollers and kind of squash it into the shape we want. We don't take steel away. We don't add steel to it. We just squash the chunk of steel we have into the shapes we want. So you can see it in a hot roll press right here, and it goes back and forth again and again and again. I wanted to try to find some images of this or a video, but it's really hard to get the contrast because the plants are so dark and the material is so hot that any videos are really somewhat useless. You can normally tell a hot rolled section because any interior corners, so these little bits right here, and even the bottom side of this are rounded. The top side edges and the bottom side edges will be sharp. So anything where it's actually been deformed will be round. They usually have, they're usually kind of blackish in color. When they come out, they have some kind of slag left on them, which is kind of a little bit of kind of burnt off material almost. We usually don't like to just leave it exposed because it looks kind of dirty and it rusts really easy because of that slag, which means it usually needs to be treated. Cold rolled is literally where we take flat pieces of steel and press them into the shape or bend them into the shape we want. So here is a piece of metal roofing. You can see it's being pressed into shape without being heated up at all. One of the interesting things about hot rolled steel is we actually change its properties a tiny little bit. We change its yield strength, just the tiniest little bit, because we've heated it up so much. We've kind of messed with it, just the tiniest little bit. So cold rolled will actually end up being very shiny in appearance, so it looks pretty nice without doing anything at all. Okay, what are the steel sections? So you can see a cool little image here of a few different types of steel sections. So W sections. W sections you would think we would call eye sections, because look at that, they look just like eyes. Now I can tell you that way back in the day, like 100 years ago, there were other sections called I-beams. These were the wide flange sections, and this is where they learned to roll them better in a plant. So these were the fancy new beams that not everyone used. So they couldn't call them I-beams because I-beams was already taken. So they called these wide flange sections. Slowly, the wide flange sections replaced the I-beams as being useful, and we don't really use the I-beams at all, if you can even find them anywhere. But that means we're left with W sections, or wide flange sections, as the name for the most common steel member we use, even though it looks like what we would want to call an I-beam. So the naming convention. So for example, if this was a W150 by 30, here's what that name tells us. The W is telling us it's a W section, or a wide flange section that looks like this. The 150 tells us it's around 150 millimeters deep, not exactly 150 millimeters deep. It's pretty darn close, but there is a varying range of depths in the 150W category. Remember that hot roll press, how it was moving the steel around? Well, some of it is, it's taking a certain amount of steel and pressing it, and they have like kind of jumps in the press sizes they use. And so the 150 press size uses a different amount of steel, and how much it moves in that press changes. But it started out, or they're all around 150 millimeters deep. The weight, though, is 30 kilograms per meter, or really close to 30 kilograms per meter. You can look up the actual weight, but it would probably be like 30.1 or 30.4 or 29.8, something like that. So the name of a W section tells us the approximate depth and the weight. And remember, the goal of this is we want to build, or if we have this design idea and we want it to stand up for life safety and we want it to work for deflection, so those are all three very important criteria. After that, we want it to be the cheapest it can possibly be. We want it to be safe and our design without sacrificing cost as well. So we want the cheapest section that works. Most materials, you can judge how much they cost by their weight. Now, that's not exactly perfect, but if you had a beam that was 35 kilograms per meter versus 30 kilograms per meter, we could know which one was going to cost more. We don't know what the cost is, but we could know which one would cost more, because the 35 kilograms per meter has more steel in it because it weighs more. Therefore, it would be the more expensive one. Channels. So channels look like half of a wide flange section. Architects like these especially for stair stringers. This nice sharp edge works really nice for certain things. The shadow cast is nice. So channels are used a lot for miscellaneous metals, which means not the main structure but the backup bits. So feature stairs or even non-feature stairs, kind of any sort of industrial stair you've ever seen probably has channels as the stringer. The naming convention is exactly like a W section. The C tells us it's a channel. The first number tells us the approximate depth, and the last number, the second number, tells us the weight. There's no real dimensions in this, but it does give us a weight that lets us use it for cost comparison. Angles. An L102 by 76 by 9.5. The depth is 102. The width, B, right here, is 76 millimeters. So we have a 4-inch by 3-inch angle. And the last number tells us it's 9.5 millimeters thick. So it tells us real dimensions, but no weight. But if we had, it becomes a lot easier to know what the relative costs are without needing to list the weight. So if we had an L102 by 76 by 4.8, that means it's the exact same thing, but it's not as thick. Which one's going to weigh more? The 9.5, exactly. So all of a sudden, it's a little bit easier for us to tell which ones are going to be heavier in the angle category. So they don't include the weight, they tell us the exact dimensions. HSS sections, hollow structural sections. Now, there are three main types. I'm sorry, my voice is going in and out a little bit. I keep trying to clear my throat, hoping it's going to make it a little bit better. Round HSS, square HSS, and rectangular HSS. Now, HSSs are cold formed. They are not hot rolled in a press. So they take a flat piece of steel and they either curve it or bend it into shape with a break. So those would have slightly rounded edges simply because we're trying to bend a piece of steel that has some thickness. If you've ever tried to bend a thicker piece of paper, it's a little bit harder, or you get some distortion at the corners. And then there's usually a seam weld somewhere on these members. So there's a side that will have a weld down the full length of this member where they took this flat piece of steel and bent it into shape. The naming convention is the dimensions. So the depth for a 152 by 102 by 6.4, the depth is 152. The width is 102, and the wall thickness is 6.4. We get real dimensions, but not the weight. So, what's the difference between D and B with an HSS? And what if it's square? Well, it doesn't really matter if it's square. D and B would be the same. Around HSS, we would really only have D, which would be diameter, because it's going to be the same in any kind of or in any sort of kind of pie cut across that circle. The rectangles, we always list the longest side as the depth. If we needed to turn it on its side, we would say long side horizontal, or long length horizontal, or LSH, something to indicate that it's turned on its side, but we would still always list the longer dimension first for these. All right. In going back to these, I think this is the best place to mention this. In the assignment, you have a series of members where it asks you the depth, the width, the thickness, and the mass of the elements. I have uploaded for you, let me see if I can pull it up. I should pull it up. Bear with me here for a second. Let me find. I'll just pull it up for you because I think it would be helpful for you to see it with me here. Oh, I forgot that I changed where I store all these. Hold on one second. Steel sections, okay. Once it opens up, I'll move it over to the other screen and show you. I have uploaded a file called Steel Sections for you. Okay, let me just... All right, so let's go back to the beginning here. All right, so here, for example, let's come up just a little bit further. All right, look at this. We have a W610 by 92. Tells us the weight in kilonewtons per meter. That seems handy. We have all kinds of other weird properties here. IX, SX, RX, ZX. We don't have a flipping clue what any of those mean. Maybe next week we'll figure out how all of those are useful. Look at this. We have nominal mass, theoretical mass, depth, flange width, flange thickness, and web thickness. So we have some information here that we can pull off. So we have nominal mass, we have the depth, the width, and some thicknesses. I am going to ask you these in the assignment, and I'm expecting you're going to these charts and looking these things up. Okay, let's jump back to this. All right, rules of thumb. We're going to introduce those now, which is also a file that's been uploaded to Quirkus, and I'll pull that up in just a minute. But these are the kind of things that you can size based on the sizing guidelines. You are not going to know if it's a W150 by 21 or 37. That's not the sort of information you're going to get out of your sizing guidelines. It's going to tell you you need a member that's around 150 millimeters deep. Well, great. You know a W150 is around 150 millimeters deep. So perfect. You could put something like that on your drawing set, if your sizing guidelines tell you you need something that's around 150 millimeters deep. So how do we use our sizing guidelines? So these are the sort of things I'm expecting you to pull off for sizing guidelines. Okay, what are some other kind of uncommon steel sections? Because there's a lot, and you'll see if you look through that steel sections file, I only talked about W sections, channels, angles, and HSSs, but there's all kinds more that I do not expect you to make use of in this course, but they exist. So we have HP shapes, which are very heavy eye shapes. M shapes are very light eye shapes. There are something called super light beams. S shapes. So these are eye shapes with tapered flanges. Wonder if I can. They have very kind of distinct. They're so chunky in shape that they almost look like an hourglass at the top and bottom, or a trumpet, if you will. Channels, there's a second category of channels called MC channels, which we use all the time as well. They were specific to something at one point. They're called miscellaneous channels, but they have strength and properties. So most engineers will use channels or miscellaneous channels equally. We have cold formed sections called CFCs and CFZs. Those are usually Girts on the outside of the building, and they usually look like, and they're very lightweight. You can like usually go to Home Depot or something and buy these. So those would look like something like that, for example. You can see a channel and a Z girt. And those would be cold pressed into shape. They're not very strong. They're good for very light work. And then a WWF is something we have if we have steel, if we have members that we need that the normal steel we have available doesn't work, we have to make our own. When I was somewhat junior at Blackwell, we had a project that just normal steel didn't work, and we were like, maybe we should just, we know that they exist, we should make our own. But they were really only used kind of like in the high-rise construction or really kind of heavy-duty construction, and we were just doing a rich person's house. So we put it on the drawings, and everyone was okay with it, even with the extra cost. I've since spec'd a lot of projects with HSS or with WWFs. So what it is, it's a wide welded flange. So it looks just like our W sections, except instead it is 3 separate plates of steel that we take and weld together. So you take a top flange, a bottom flange, and a web, and weld them all together. You can imagine they're expensive, but we can get massive members all of a sudden. I've designed wide welded flanges that are 2 meters deep, so I can literally stand in between the flanges of a WWF that's large. All right, you guys remember this image? This is our full stress strain curve for steel. Remember, I love this question. It's going to be a great exam question where maybe I tell you to identify what on this is E, what is the yield stress, what is the ultimate stress, what is the strain at rupture. Oh, one of my titles is missing here, so I'm just gonna fix this slide. That's kind of weird that disappeared. So slide 11, stress axes. So this is our strain on the bottom and our stress on the side, and we've plotted the stress versus strain all the way through the testing of a piece of steel to develop this stress strain curve. Typical steel properties. So as much as we're talking about 350 MPa steel, So for a cold section, our FY, or our yield stress for steel, remember, we don't want to go past that. That's as much as we have this maximum up here of stress. After this point, we're getting really large, ugly, nasty, big deformations that are permanent in our steel. So we don't want to go past this. Remember, if we want to know the capacity of our steel, yeah, great. All along here works. We're good. We could test all of this and we know that we're okay. But what we want to make sure is that we don't go past the maximum stress on our steel. Doesn't mean we want to hit that stress, but we know that that's the maximum stress. So if we make sure something at the verge of failure is still okay to support the loads, we know anything below that will still work just fine. So we usually use our FY to verify that we're okay. So FY for cold formed sections is 350 MPa. So, but as much as it's 350 MPa steel, for a hot rolled section, remember we heated it up red hot and we did some weird things to it? Well, that lowers our yield stress just a tiny little bit. It takes it down to 345 MPa. FU of 450 MPa, we don't use very much. We'll use the ultimate capacity of steel in some very specific applications like bolt connections and places where we're worried about very certain types of failure. E of steel, you know, it's 200,000 MPa. It's the one that I need you to know. I don't make you memorize the rest. G is a really weird property that has to do with the fact that as much as I've told you that when we're talking about strain, things just deform, G has to do the fact with, if this is my eraser, when I squish it, I've squashed it down, but I get a tiny little bit of bulging on the side. That little bit of bulging we've ignored so far, but it does exist, and that is called, or that's built on this premise called Poisson's ratio, and G is a property that relates Poisson's ratio to E, again, a property way beyond what you need to know, but I'm going to give you the value, because it can be derived by knowing these other things. So we've talked about these and we know where they come from, so I'm just going to tell you this is derived from these other elements. Remember, I love lists. Lists make great exam questions and quiz questions and assignment questions. So what are the advantages and disadvantages of steel construction? I happen to do a lot of work in steel. That's my primary zone of work. That doesn't mean steel's always the right answer for everything. So one of the jobs you need to know, because remember when we talked in that first lecture, that before you even sit down with an engineer, you've usually already picked your material and you've already done some preliminary sizing. And so today we're going to talk about why you would pick a particular material for steel, and then we're going to talk about your preliminary sizing. So steel, it's very strong. It's one of the strongest materials we work with. It's very stiff, so its E is very, very high, and it's light. And you're thinking, what? That doesn't make any sense. How is it light? It's really heavy. It is really heavy as a material, as a component of material. So if I took a block of concrete and a block of steel and a block of wood that were all the exact same dimension, yeah, the steel's gonna weigh more. But remember how I said it's strong and it's stiff? We need very little of it to do the exact same job, which means the building use of steel to hold up the building and the things ends up being very light. So the amount or the weight of steel we need to do all those jobs is relatively low because it's strong and stiff. Okay, it can go for very long spans, and we can make it very tiny steel columns if we're dedicated and we do the work to make it happen. And when I say long spans and small columns, obviously I'm talking relative to other materials. And so in 2 weeks we'll talk about wood, and then in 5 weeks, 4 weeks, we'll talk about concrete. Has really great quality control, both in the material and in the construction. So the material itself has chemists sitting there testing every batch of steel. So when we say that we have 350 MPa steel, it's a pretty tight range. It's like it's between like they're very specific guidelines. Like it can only go down to, I think, 340 as a one-off batch, and the statistic probability of being in that. So a specific plant can only make so many in a year that are that low. And then it can go up quite a bit higher. Except for HSS steel, there are specific guidelines for it that it can't be too strong either. And you're thinking, why would too strong be a problem? We would always want it to be stronger than it could be. That's true unless we're talking about capacity design. And capacity design is this part of seismic design where we absorb energy while our steel is yielding. Remember, if we came back to this stress strain curve, this massive deformation, if we let it to deform all the way up to here and snap back, that was our potential energy, and all of that portion of the curve was actual dissipated energy. Not dissipated, but it went into moving that object. So if we can absorb a bunch of energy in seismic design, we would like to do that. But if it's too strong, it could actually be a problem, that it doesn't deform the way we wanted it to. So certain elements in steel actually have an upper bound as well as a lower bound. Then the quality control on site, well, there's a really rigorous process with steel. The project drawings go out, a steel fabricator looks at them, they have their own engineer that designs all the connections, or where the things go together, how they connect together, and they produce a set of shop drawings. They get sent to me or the engineer. I look at them and say, yes, this is what it was supposed to be. No, this isn't what I was expecting to see. And so there's that process that we actually get to kind of see the building before they make the building. And then when it's being erected on site, the steel goes up and it's kind of sitting there exposed with most of the elements up, where you can go in and with a tape measure I can be like, yep, that's a 150, that's what I wanted. Oh, look, you're missing a few bolt holes there. That doesn't look like the moment connection it's supposed to be. So it's really easy to visually see if it matches what the structural drawings were. Things like concrete are a little bit harder to see because there are elements buried inside the concrete. And wood, it's hard to see where the nails are and how the connections happened all the time. Steel goes up fast. If you have a good fabricator or a erector, you can do a floor a day on buildings. All of the work is prior to getting to site. Future alterations are really easy. In all of my scrap paper, I've been using it all up. If we have two walls like this, and one is steel and one is concrete, if I was there in person, I'd be drawing this and it would be up on the screen for you guys and you'd be seeing me actually draw it because I have a pen that works with my computer. I have a very expensive computer specifically to be able to do that. So if these are our two walls, our steel, there's very little steel in that wall that's being our lateral load resisting system, or the thing that stops it from kind of just tipping over. The concrete is a solid wall that is structural element. If we came in after this and we decided, oh, this is a problem, we want to move the door from this side to this side. Well, in the steel, maybe we could move it a little bit. In the concrete, anything we do is a huge amount of work. Or if we have a wall that didn't have a door and we want to come in later and put a door in. Steel, we can go look at the drawings, we see where there's no steel, and we can just bust out the drywall, pop a door in. Concrete, you're talking about structural work. Fabrication benefit, because we can fit things up in the shop, and it is always cheaper to do work in the shop. As much work as you can in the shop lowers the price of your project down as much as possible. There's a fabrication benefit of trusses in the shop, where we can take small elements and put together bigger elements of steel. Steel is non-combustible, meaning it doesn't burn. It itself is not a thing that will burn. Let's come over to disadvantages. I'll come to long lead time in a second. It has a poor fire rating. That means as much as it's not going to burn, it doesn't do well in fire. Steel, when it's exposed to high heat, actually loses its strength properties because we've actually lowered it so it's not as strong as it was. So in a fire, and we have fire ratings that tell us how long a building needs to be able to stand to allow people to get out of it in the event of a fire. If steel essentially melts, I mean, it's not really melting, but we're heating it up so hot that it's not as strong as it was. Steel doesn't do well in that situation. Steel has a long lead time. So remember all that shop drawing process and the review that I talked about? That can take months. So there can be what appears to the owner to be a long delay, and then all of a sudden the steel is on site and the building's being built. Concrete, you can mobilize almost the day after you've decided you're going to build your building in concrete, but it's a really slow process to build it. Some financing, and this is why it's important to know your client and your owner of the building, because some financing situations will only pay out money to the owner based on visual progress of the project. Which means if everybody's been working their butts off for months and months and months, but there's not a thing done on the site, there's no money to the owner who's trying to pay everyone to do everything, and we're months into the process and nobody's gotten a check, that can be a problem. And then all of a sudden the steel goes up. So the kind of full construction time from we're hiring you to this building is built is probably pretty similar in steel and concrete. But what chunk is on site and what chunk is off site varies. Because steel is strong and stiff, which means it's light as a building as a whole, we don't have a lot of material that's doing the work to hold our building up, so vibration can be a real consideration. And then the last one is depth. We have deep members in steel. Let me just draw you another little picture. I set all of this paper here to be able to have things to draw for you. Okay, I'll do this one in red. So we have deck, and we have joists. I know you guys can't see what I'm drawing, but you'll see it in just a second, I promise. Thought I just heard a small child wake up. Okay. So let this get into focus. Okay, so you can see the red here. Steel, you can see we have a very shallow depth for the most of it, but we have our joists that are quite deep versus concrete, which in spots is deeper and spots is shallower, but overall it's kind of consistently the shallower depth. When do we use steel? Why would we use steel? Well, we use it for very low and very high buildings. The sweet spot for concrete is kind of, you know, greater than 4 stories, up to about like maybe 30 stories. Anything kind of outside of that range, we're talking about steel. Steel is great for shopping centers, hospitals, schools, warehouses, and industrial buildings are almost only built with steel. And systems buildings. So what's a systems building? A systems building is a building by a specific fabricator that build a specific type of building. I don't know how many of you play hockey, for example, but most communities have a Butler or a Balin building as the hockey arena. So these aren't the like community centers where you have your pool and your hockey arena and all of the bits. These are usually kind of one-offs just for the hockey arena, and you've probably seen them because they tend to look I'm going to draw one here, and we're going to see pictures of them in a few minutes. So they tend to look like this. So the blue is the steel. Those would be arches that happen every few meters, probably like at 8 meters, maybe 9 meters on center. And then kind of some sort of decking or girts or wood framing going from frame to frame. Okay. This is where we're going to get some answers. They're not the final answers. They're not the engineering answers. So this is not engineering. This is sizing guidelines. This is what you, the architect, needs to know. And I'm going to tell you, most engineers tend to forget these rules, which is really annoying for you guys. You guys should know these better than your engineer. You have available to you a list called sizing guidelines. Let me open it up. Okay. You have this document called Sizing Guidelines. These are guidelines for estimating member depth in relation to length or height. These are guidelines. They are not rules. These are not the right answers. They're pretty darn close to the right answers, which means you can work with the owner very early in the project without hiring an engineer, and you'll be pretty darn close to right. They assume normal conditions in a normal range of applications. So we are not talking about building the fancy things. We are not talking about pushing boundaries. If you're pushing boundaries, these guidelines will not apply. If you're not in a normal condition or application, they won't apply. If you are outside of normal, cost will not be linear. So if you think you need something twice what these guidelines say, the cost is not twice. It'll be more than that. If your gut tells you that something seems too good to be true, it probably is. If your sizing guidelines tell you something and you're forgetting the fact that it's outside of something that is normal, and you're like, wow, this is great. I love this. This is way smaller than I expected. You're probably right. It is smaller than you expected because it's too small. So kind of give yourself a healthy gut check. Now, mine are developed kind of within the Blackwell office and over my years of practice. There are other ones you can find on the internet that will be very, very, very close to this. So I'm not talking that mine are kind of way out to lunch doing something completely different. They will be, you know, plus minus a few percent from what mine are telling you. But because we need, and you're welcome to use those kind of going forward in your career. If you find someone else's sizing guidelines handy to use, I have no problem with that out in the world. But for the explicit use within this course, I need you to use these ones so that we can kind of standardize our answers. Where we're an asynchronous course online, if I'm testing you on something, we have to all be using the same standard. So these are the sizing guidelines that you have to use during this course. Cantilevers. You use the length of the cantilever, but half of the listed ratio. So whatever it says The sizing guideline is you can use half of that guideline if you're talking about a cantilever. And we'll talk about that as we get into the sizing guidelines in a little bit. Okay, so I think we've talked about all of these things. This is your gut check, everything you need to know about structures you already know. These rules are based on that. If it seems too small, it probably is. So again, these are totally empirical. These are not scientific. These are based on the fact that in a normal range of things, depth and length are a linear relationship. Next week, I am going to do a lot of math that you don't have to do to prove that this is bullshit. Depth and length are not a linear relationship in structural engineering. They're just not. But in a huge range of applications, the normal range is pretty small, and we can use a pretty good representation of that relationship as linear. So if something's linear, it's a very simple way to relate two things together. This becomes the slope of a curve. We are going to know that this is only applicable for preliminary sizing of elements. Okay, so depth to length. So if we want to know how deep a beam needs to be, so if we came, well, I'll show you some of those in just a minute. If we know how long it is, and remember, we're the ones creating these plans. We're the ones creating these buildings, so we're the ones picking how long it needs to be. You notice there's nothing about loads in here. We've spent all this time talking about loads, and this doesn't talk about loads at all. This is where understanding what is normal is important. If you know you have a building with ridiculously high loads because it's supporting, I don't know, a gold factory, you would know that these sizing guidelines don't apply. There's nothing about loads in here. So obviously this can only be talking about normal loads. We would take our length and divide it by our rule of thumb, and that would give us the approximate depth we're expecting to see in that design. We know it still has to be engineered, but it's going to give us a pretty good thing to put on our drawings very early on. Now you're wondering, why do I care what the heck I put on my drawings very early on? Well, if you have a building that has a maximum height of, let's say, 10 stories, and, or sorry, not 10 stories, of so many meters. So you're so many meters tall. You've got a hard limit on how tall this building could be because the city has said nothing taller than that can be built. And that is a real thing that most cities have. I'm from Halifax. Nothing can block the view from Citadel Hill. In Ontario, your shadow cast, how long your shadow cast is very important. So there are hard limits on how tall buildings need to be in certain areas in the city of Toronto. If you draw that all of your steel needs to be 150 deep, and you set out your story, so each floor needs 150 millimeters for the steel supporting structure, for example, and you're putting in all the stories you need to put in. When it comes time to do the final engineering, you find out that each floor needs steel that's 500 millimeters deep. Well, maybe all of a sudden now you don't have enough headroom on each story, which means you have to delete a whole story of your project. For an owner, knowing how many floors they have means how much revenue they have coming in, which means now all of a sudden the building is not feasible. It's just not economically feasible for the owner to build it. So these are really important things within the decision-making process. So having a good idea of how deep your floor assembly is very early in the project is very important. Obviously, there will be elements. Maybe you have one or two beams that are outside the range of normal, and maybe those can be dealt with locally, but it's not going to be the thing that shuts down a whole project from happening. And that is a thing I have seen happen in Toronto. All right, if we know we can have a maximum depth of, I don't know, let's say we have a project that has a maximum depth of 400 millimeters for our steel assembly. Well, then we can use our rule of thumb, and that will tell us what the maximum length of beam we could have. And if we know the maximum length of beam we can have, then we know where our columns or other things that need to support it is. Basically, that could tell us our grid assembly. When do we use our structural guidelines, sizing guidelines? They'll be close to the final designed member when we are within the range of normal applications. I know I've said this a bunch, and I think it's really important for you to hear it again and again and again and again. That means these rules stop being helpful if we're outside the range of normal. So what's outside the range of normal? We have really, really high loads. So something outside the range of normal, like an MRI machine, for example, Olympic weightlifting unit. Those things are outside the range of normal. If we're spanning really large distances, these sizing guidelines are meant for conventional construction of buildings. So we're not talking about 20-meter spans. If you have a 20-meter span, you can use your sizing guideline, but then you should know, maybe I should bump this up a little bit. If you're using a unique layout, maybe things are skewed on an angle. All of a sudden, these sizing guidelines might not be the best solution. If we have a really large transfer, so if we have 20 columns coming down 20 floors, and then on the bottom floor we only have 2, there's something there picking up the other 18 columns. That would be a really large transfer. That beam or truss that's picking up all of those columns that are supporting all of those floors above aren't going to follow the sizing guidelines. Or if you're using the material in a unique way. So if you're doing something with this material that is outside of its intended use, these sizing guidelines aren't going to apply. So let's start taking a look at some of these things, as well as drilling down into what the components of steel construction is. Well, for steel itself, we have 2 different decking types of surfaces, and they're the first thing, like they're the top thing. They're the thing that your flooring goes on or your roofing goes on. So they are kind of the lightest part of your steel construction. They're the thing that covers every surface that supports your kind of roofing element and your water membrane, the stuff that protects you from the elements, the stuff that, you know, protects people from just dropping through the floor onto you. It's not that other things aren't strong enough to hold them up, but you need a place to put your foot on every individual step. Deck spans in this direction. So this is corrugated metal deck, and it's spanning in this direction. What does that mean? Well, if I have this piece of paper and I am spanning it from one hand to the other, you can see it's really flimsy. If I had this and I fold my paper so it's spanning the same distance, the length of the span is the same. If I corrugate it and it doesn't blow off my hands, look at that. It's spanning the same distance just because I've corrugated it, and it doesn't flop down through my hands. So the direction of corrugation is really important. If the thing that's supporting these decks is parallel to the flutes, it doesn't do anything at all. So you can practice that if you want. Take a piece of paper, fold it, you'll see what I'm talking about. Now, we can use sizing guidelines that tell you how deep our deck needs to be, but it's a manufactured thing. There's only so many sizes available. So typical deck is 38 millimeters. This is the absolute norm. We can get it in 76 millimeters deep or 3 inches thick, but 38 millimeters is the most common and it's the cheapest available. It's typically 0.91 millimeters thick. Remember when we were looking at dead loads, there was steel decking, and there was, you know, if it's 0.91 millimeters thick, and then there was a heavier one. Well, the one that is common is, so the most common deck is 38 millimeters deep, and the steel that's bent into that shape is 0.91 millimeters thick. Span of deck usually sets how far apart the purlins or the open web steel joists are. So my hands in this example are our joists or our purlins. They're the things supporting our corrugated metal deck. Our deck can span its length divided by 50. Now, we already know the most common deck is 38. It looks like we could work this backwards. Anyway, let's go to the next slide and see what comes up for us. Okay, if we have joists that are 2 meters on center, so there's 2,000 millimeters between each joist, or if we were talking about the paper as the metal deck, how far apart my hands are. What depth of deck should we use? How deep does our deck need to be? Well, we know its length is 2 meters. Our sizing guideline is 50 millimeters, 50, it's not a unit, it's just 50. 2,000 divided by 50. Well, let's just take a look at that. 2,000 divided by 50 gives us 40 millimeters. Okay. In the next sizing guideline, I'm going to tell you to never go with something less deep than this number. But in this sizing guideline, I'm going to mess with you and I'm going to say it's okay. I know. I'm a pain in the butt. I know it's really annoying, but it's 2 millimeters. It's like the tiniest little bit over. What was our most common deck size? Yeah, it was 38 millimeters deep, or 1.5 inches thick. So we're saying deck that is 1.5 inches deep, or 38 millimeters, can span pretty darn close to 2 meters if the loads are normal and there's not weird things happening. So deck comes in 38 and 76. The 38 millimeters is very close to 40 millimeters. We should use 38 millimeter corrugated deck most of the time. That's what we should be using. So if we had 38 millimeter deck, we know that 38 times 50 is, I know it's not quite 2,000, but pretty darn close to 2,000. This means that whatever supports 38 millimeter deep corrugated metal deck should usually be around 2 meters on center. So that's just, all of a sudden, if metal deck and joists or purlins are the biggest component of steel construction, you already know a huge amount of steel construction practices. You're going to have supports for metal deck at 2 meters on center, and your deck's going to be 1.5 inches thick. All right, what about corrugated metal deck with concrete, or composite deck? Sometimes you'll hear this called composite deck. I'm actually going to add that in here for you. So slide 20, add. So sometimes you'll hear it called composite deck, or concrete on metal deck, or concrete on corrugated metal deck. Those are all other ways to talk about it. We are saying, when we talk about the depth, the total depth. The deck is the same piece of deck that we used in the last example. They just punch a few little holes in the side, and that's just to kind of grab on to the concrete. We want the concrete to kind of hook into that, to join them together. We want to make it composite. We're going to talk about that in a few weeks, what making something composite means. So remember, it's the same 38 millimeter deck, while the concrete can vary, but there are standard practices. The norm, the most common thing in the whole frackin' world for concrete on metal deck is a total assembly that's 102 millimeters deep. If we've got 38 metal deck, that means we're talking about 64 millimeters of concrete above the top of the metal deck. Yeah, we've got concrete here in the flutes, for sure. There's more in there. All right, we are talking about normal density concrete on 38 millimeter deck. Span typically sets how far apart the purlins or open web steel joists are. Because now, what we're really talking about is this filled with, I don't know, Jello? We put this in a pan and we fill it up with Jello and then take it out? Something along that lines. So we're still talking about how far apart the things that support it are. So the sizing guideline is the length divided by 20. If the joists are at 2 meters center to center, what depth of deck should we use? All right, we take 2,000 divided by 20, we get 100 millimeters. Well, the most common concrete on metal deck is 64 concrete on 38 metal deck, which tells us that we should use 38 millimeter deck with 64 millimeters on concrete, which is a total of 102 millimeters deep. This is the most common composite metal deck system. Again, this means whatever supports the system should occur every 2 meters. Now, when we're in person, somebody always at this point asks me, why can the thing that's 38 millimeters and the thing that's 102 millimeters with the concrete on it span the same distance? Why would we ever use the concrete on metal deck? And this is where knowing that these are in normal applications is useful. If we're talking about concrete on metal deck, it's usually the floor system, which has higher loads than our roof system. The metal deck on its own is usually our roof system. So if we're talking about these being used in the range of normal, these sizing guidelines know that we're talking about different loads. Even though there's no loads in these calculations, we know that metal deck by itself is normally a roof and concrete on metal deck is normally a floor. So for both systems, so our roof and our floors are going to have a decking system on them, and the things that support it need to be around 2 meters on center. Now, those things that support it can be one of 2 things. It could be an open web steel joist, or it could be a purlin. So let's talk about what those 2 things are. The first one is an open web steel joist. You've all seen them. You might not know what it's called, but this is typically what an open web steel joist looks like. We have a top chord and a bottom chord, and we have our web elements. We now know that if we knew what the load on this was, we could figure out the internal axial loads on all of these members. But we're not going to do that. We're now trying to talk about sizing guidelines. Okay, the sizing guideline for an open web steel joist is the length divided by 16. Now these are made by a manufacturer, and so these are engineered by someone else. I, as the building engineer, wouldn't engineer these. I would look up ones that work, so I would go farther than these sizing guidelines, but it's not that much more than what you would do as the sizing guidelines. The sizing guidelines are pretty darn accurate for open web steel joists. They tend to come in 2-inch increments. So you're not going to get an open web steel joist that is 272 millimeters deep. It would be 250 or 300 millimeters deep. So we're going to want to know that because we don't want to write weird things on our preliminary drawings. We want to write real things that exist. So let's see what that means. How deep do joists need to be if they're spanning 9 meters? So as much as this was our deck, we know our deck is spanning 2 meters. So I have these things that are picking it up that are every 2 meters apart. But now I need to know how far those things can span, or how long those can be, or how deep they need to be to do all this work. We've been told these joists are 9 meters long. How deep do they need to be a normal assembly, which means they're probably supporting metal deck or concrete on metal deck? Well, we have our length. We know what our sizing guideline is. So we take our length and divide it by 16. We get 562.5 millimeters, which is great, but we would never, ever, ever write this on a drawing. We know that they come in 2-inch increments. Would we write 550 or 600? Remember, this sizing guideline is telling us how deep something needs to be at least. If we have something deeper, that's good. Something shallower, not good. We could get a nasty surprise when we do the design. That means we should go with the next 2-inch increment upwards. So we should go with a 600 millimeter deep open web steel joist. I could put 550 on the drawings. For sure I could. But what if I did that and the engineer comes back and says, no, they need to be 600 millimeters deep. It doesn't work at 550. So 2 inches, not a big deal. But if we had that on 30 floors, for example, that could really start to add up. And maybe that's an elimination of an entire floor of our building. So if we have open web steel joists that are probably 2 meters on center because they're supporting deck of some sort, they would need to be 600 millimeters deep. So assuming it's picking up 38 metal deck or 64 concrete on 38 metal deck, how often do we need them? So we're going to use a 600 deep open web steel joist at 2 meters on center. So this is what we would put on our preliminary drawing set. If we know that we have a grid system, or our elements are spanning 9 meters, we would have 600 millimeter open web steel joists at 2 meters on center, probably supporting 38 metal deck if it's the roof, or 64 concrete on 38 metal deck on the floors. We've got most of our building done. We're almost there. We're pretty close to done now. Okay, beams. Beams. Remember I talked about tributary systems? And I said if you came across a river in the middle of the forest, you don't know if it's a river or a creek or a brook because it doesn't matter. They're all a river. Well, all of our things that aren't a truss or an open web steel joist, all of these bending elements are a beam. We, to help us figure out how deep it needs to be in a preliminary aspect, give them some other names because it tells us some things about them or what they're doing. They're all still beams. It doesn't change the fact that they're all still beams. We kind of have like a subset of names within our beams. We have purlins, beams, and girders. All beams, all still doing the same job. If we came across them in a building and I pointed to a particular one, I would call it a beam. It wouldn't matter that it's a purlin. I would call it a beam. I need to know it's a purlin when I'm using my sizing guidelines. So what's a purlin? What's a beam? What's a girder? Okay. We have different sizing guidelines for each of them. Beam width. B equals 2 divided by D or D divided by 3. I hate this sizing guideline. It's a crock. It's just to give you something to draw. This gives you no real information, but it helps you draw a pretty picture on your drawings. So beams come in standard sizes listed in the steel handbook. The W sections, channels, and HSSs would be the most common. B is very inaccurate and only a very, very rough guideline to give you something to draw. So all the things I just said, you have that list. Very early in this lecture, I gave you a list of what members I would expect you to put down on a drawing set based on these sizing guidelines. So whether it's a W150 or a W460 or a W610, I'm not looking for the second part of that information. You can't tell that based on sizing guidelines. You can just tell approximate depth. All right. You're going to use a purlin sizing guideline if your beam is supporting deck and occurs around every 2 meters on center. So it's the normal, most common thing. It's not doing a big, heavy job and it's fairly repetitive. You would use the beam rule of thumb if it's supporting the purlins or open web steel joists. So if it is a beam section that is supporting the purlin beams or the open web steel joists, you're going to use the beam sizing guideline. You would use a girder sizing guideline if the beam is doing something extra. So maybe there's a point load on top of it. Maybe there's another beam framing into it. So if you want to think about it as them all being beams, the purlins aren't working very hard, the beams are working about normal, and the girders are working just a little bit extra. And that is how, and so, you know what? It's almost better if you don't call them purlins, beams, and girders. Call them a beam not working very hard, a beam working about normal, a beam working really hard is another way you could almost think about it. How deep do our purlins, beams, and girders need to be if they're spanning 8.5 meters? So if we have a bunch of elements that are all spanning 8.5 meters, but they're doing different jobs, Remember, the Purlin means it's about every 2 meters on center, and there's a bunch of them, and they're just supporting metal deck. So they're just picking up the nice, light, easy thing. You could use them interchangeably with open web steel joists, for example. All right, so for a Purlin, we have our 8,500 divided by 25. We need something that's 340 millimeters deep. We could look at a channel that's 380 or a W360. Notice it is not a W340. It is not a W310. We want to go up to the next one to a W360. If we had a beam, we would have our 8,500 divided by 20, and we would need a W460. Now, if we were looking at a plan, we're not looking at a plan here, so we don't know if this thing is a Purlin or a beam or a girder, so we're sizing it all ways. If we were looking at a set of drawings, we'd be able to see what this thing that is 8.5 meters long is doing. If we saw that it was working really hard, we would probably call it a girder. And if we called it a girder, it would be the length divided by 15, or we get 567 millimeters, meaning we want a 610 for this element. So if the Purlins were supporting 38 millimeter deck or 64 concrete on 38 millimeter deck, how often should they occur? If they were supporting concrete on deck or metal deck, they would be a C380 or a W360 at 2 meters on center. That would be pretty normal for something we'd see on a project. So trusses, we would often use them instead of girders. So you don't use them lightly. You use them, there's a manufacturing cost built into trusses. So we use them when we have something working very hard or when we're outside of the range of normal, because we can build this to be what we need it to be. You wouldn't usually just go into a project and replace the purlins and the beams with trusses. You would go in and maybe replace a girder with a truss, because in the end it's lighter and maybe the elements for girders just don't exist. So these are made by manufacturers, but unlike open web steel joists, they'd be custom. So we'd still typically specify something in 50 millimeter increments. So what size does a truss need to be if it spans 8.5 meters? Our sizing guideline is our length divided by 12. So we would get something that is 708 millimeters deep. We want it to be, it would be silly to, you could put 708 on the drawings, but you wouldn't. You would never do that. That just isn't something you'd see unless it was, especially not in a preliminary stage of your project. Maybe in the actual contract documents because there was something super specific, but we'd say we need a 750 deep custom truss. Now, our girder was a W610 and our truss is 750 millimeters deep. Why would we make that jump? Well, a 610 is a deep chunk of steel that's solid. A truss has some openings in it, so maybe we can pass a duct through. Otherwise, we have to go underneath with our duct. So yeah, we're making it deeper, but we're making it deeper, we're making it less deep for the overall system. Let me see if I can find a piece of paper to draw you one more pretty little image here. My kids wrote all over a chunk of this stuff. Okay. I'll show you what I mean with that then. All right, if we had a W360, or sorry, W610 duct, and then a truss that's deeper. So, not drawn beautifully to scale, but pretty darn close. You can see we have a W610 with a duct passing underneath it. And so as much as our 750 truss is deeper than the W610, it's not as dropped down as it would be for the duct. So that's why, that's one of, there's other reasons, but that's one of the reasons why we might switch over to a truss. Okay, columns. We would not use an angle or a channel as a column. You guys are going to use the h divided by 20. Don't even worry about this h divided by 40. That's for some very weird specific things, but h divided by 20 is the sizing guideline you guys are going to be using. You heard it here first. All of your answers, that's what it's based on. For short columns, stick to h divided by 20, which are all the columns we're going to be talking about here. Standard sizes listed in the steel handbook. So stocky W sections and HSSs would be the most common. This is the minimum dimension, so that the other side needs to be the same or bigger. So if we had columns that were 3 meters tall, how big do they need to be? Well, our height divided is 3,000. Our sizing guideline is 20. We need elements that are 150 millimeters in dimension. So I would suggest an HSS 152 by 152 or an HSS that is 152 millimeters in diameter. You see, I didn't list a W section because all of a sudden the width becomes important on these ones. Remember, we need something that is 150 millimeters as the minimum dimension. So we can have W150s that are 150 millimeters deep, but only 100 millimeters wide. So for these, you'd need to get pretty particular. For the most part, I'm going to tell you to put HSSs as your answers for columns. Okay, look at this. You could also look in steel section table for W150 and is also 150 wide, but the HSS seems like a pretty good option. All right, here is a plan of a floor. It's not the whole floor. There's probably more going on here. Look at this. We've got some columns here. We've got some beams that look the same. So 2BO2 spans from C1 to C2, and this 2BO2 spans from C2 to CO1. So they look like they're doing the exact same job. Well, except that they're supporting different elements, but their tributary width looks the same and their span looks the same. We've got deck. Ooh, look at this. 2BO3 goes from here all the way over to here. There's not a column below it. CA. Do you guys remember when we looked at nomenclature very early? We said CA means column above. That means this is a very big transfer. What did I say about beams that had a big transfer on it? We probably wouldn't call them beams. We'd probably call them a girder. So it looks like, so 2BO2, they look like they're picking up a bunch of little beams of some sort. So they look like they're doing something normal. I'd call those a beam. 2BO3 looks like it's doing a big heavy job. I think I'd probably call that a girder. These ones are easy. They look like joists. So this funny little dashed line, usually in a drawing means joist, and they've said 2J01. And look here, they've told us that 2J01 is a joist. Now these beams, 2BO1, there's a bunch of them. They look like they're doing the exact same thing as a joist. What do we call beams that only pick up deck? Look at this, it's a deck. What do we call joists or beams that only pick up deck, are about some equal spacing on center and could do the same job as a joist? We call those ones purlins. So look, it's 2BO1, but I think I'll call that one a purlin. Let's come up here and see what they're asking us. So assuming the datum is 3.2 meters or 3,002 meters, that is telling us we have a ground and we have a datum that is 3.2 meters in the air. They're telling us that this floor is 3.2 meters in the air. So that is telling us that these columns are 3.2 millimeters tall. Size the concrete on metal deck 2D01, size the joists 2J01, the purlins, oh, they called them purlins too, it looks like we were right. Size the purlins 2B01, the beams 2B02, and the girder, oh, they called it a girder too, 2B03. But they're telling us to provide a truss alternate as well. and then size the columns. So we have CO1, CO2, and CO3. All right, deck, 2DO1, concrete on metal deck. They've told us it's concrete on metal deck, which means it's probably a floor, which means it's probably doing relatively normal things. Look, they haven't told us the dimension of how far apart all of these things are, but they all look to be exactly the same distance apart. We know this whole distance is 24 meters, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spacings here. So we have 24 meters divided by 13 is telling us how far this deck is spanning. So this deck, remember, it's like this. It is spanning in this direction. So it's following this. The joists and the purlins are like my hands. But we make decks in big, long pieces. So it's not how long the deck is, it's how far it's spanning. So the deck, each little chunk of deck is spanning this distance right here, or 24 meters divided by 13 spaces. So 24 divided by 13, it looks like it's spanning around 1.846 meters. Now already, let's not even think about the math for a second. Is that around 2 meters, maybe even a little bit less, which is good? Yeah, we probably know that it's going to be 64 concrete on 38 metal deck, because that's pretty much the norm. But let's do it. Let's check and see. Okay, we have our 1,846 millimeters, which is how long our deck is spanning. Not how long our deck is, but how far it's spanning. Divided by 20 gives us 92 millimeters. Perfect. We have 38 deck with 64 concrete. Now we know this can span about 2 meters. Maybe they could space those out a little bit. Maybe we could get rid of one of those. Maybe there's other reasons why they have it at that spacing. But we know that what they're showing works with the normal concrete on metal deck. 2JO1, let's just go back a second. Our 2JO1 and our 2BO1 both span 8 meters. 2BO2s span 12 meters, and then our 2BO3 spans 24 meters. Okay. 2JO1, we know it spans 8 meters. We know our sizing guidelines for open web steel joists is 16. That tells us we need something that's about 500 millimeters deep, and they come in 2-inch increments. So 500 or 50 millimeter increments. So 500 millimeter deep open web steel joists. We know that these are occurring at 1.846 millimeters center to center. There's my sheet of paper where I'm writing myself notes. I can't remember if I have that written in here for you or not. Oh my goodness, I have so many pieces of junk paper here. Where did I write that note for you? Here we go. Okay. I am going to add in slide 31 that it's 500 open web steel joist at 1,846 millimeters center to center. Do you know what some people do sometimes? We know that that's at like 1.85 meters on center. What we'll often do, if we know that this could be up to 2 meters on center, we'll say 500 millimeter deep open web steel joist at 2 meters center to center max, meaning maximum, and then we would say divide by equal spaces for the actual situation. That means if they need to move one a little bit, they have a little bit of play for something, like maybe there's an opening somewhere, it gives them a little bit of a buffer. That's often what we'd put on the drawings. So 2BO1, same span, doing the exact same thing as the joist. These two things are interchangeable, but we need a C380 or a W360 because the depth required is 320 millimeters. So again, These are shallower, but they're solid. So there are pros and cons to each one. Which one's right? Totally depends on your situation. That's not something I can tell you. For the same span, the purlins are shallower, but they're also heavier. All right, let's look at the beam. So beam 2B02 was spanning 12 meters. Our sizing guideline for a beam, now remember, a beam is the thing that is usually picking up joists or purlins. Well, we had two different 2B02s. One was picking up joists and one was picking up purlins. We get that it needs to be at least 600 millimeters deep, so we would always go up from that. And the next available W section that they make is the W610s. So on our drawings, we would say 2B02 is probably a W610, so something that's around 610 millimeters deep. This would be for your preliminary drawings. It still needs to be engineered, but this would be great for a preliminary drawing set. A girder, 2B03. Our length is 24 meters long. Our sizing guideline for a girder is 15. Well, we have 1.6 meters is our depth. There are no W sections that deep. So what are the options? We could do a wide welded flange. We could tell them to make a section. That's really expensive because we're making something. But once we're doing something custom, maybe we could do a lighter custom thing like a truss. So I am also going to add WWF there if we wanted to. So if 2B03 was a truss though, and they asked us to give a truss alternate, it would need to be a custom 2 meter deep truss. So our 24 meters divided by 12. Now there was one thing left we had to do. Column C1, its height is 3.2 meters. Remember they told us our datum, or that floor, is 3.2 meters above the one below. So that tells us we need it to be at least 160 millimeters in dimension for the least size. So we would want an HSS 203 by 203. Column CO2, same height, same thing. Well, and I'm gonna add in that. What was the difference between CO1 and CO2? Well, CO1 was only picking up half of 2B02. CO2 was picking up 2 halves of 2B02. CO2 is picking up twice the load as CO1. This is where the column sizing guidelines are kind of a load of crap because these two things are not doing the same job. This one is picking up twice the load of this one, but yet our sizing guidelines gave us the exact same size. So that's where knowing what is happening in your project is really, really, really important. Probably not a big deal for this one, but you guys remember CO3? It's picking up a lot of load. It's doing a lot of work. Maybe that needs to be something even bigger. Okay, that's all the work we needed to do today. The next part of this lecture, we're gonna look at some pictures. We're just gonna look at pretty pictures and I'm gonna talk about them. Basically, we're gonna see what some of these things look like. I've done better than I hoped. My kids still haven't woken up. I'm gonna go for it and see if I can record this whole lecture before they wake up. I let them stay up really late last night because I knew I would want to do this morning. Solid parenting. Okay, steel construction images. Look at this. We've got a metal deck. You can see it spanning in this direction. Oh, look at this. It looks like we've got some purlins here. Looks like all of these things are about 2 meters on center. So we've got metal deck spanning about 2 meters on center. These purlins span into our beams. So we've got deck spanning in this direction, beams spanning, or purlins spanning in this direction, beams spanning like this. We've got our columns picking things up. And then look at this. Look at these funny diagonal things in the plane of a wall. Those are our braces. That is our lateral load resisting system that we're going to spend some time talking about in the very last lecture. We're going to do some kind of thought process about our lateral load resisting systems. It looks like this has all of the elements of steel construction embedded in this one image. In fact, this one image makes a great exam question. Maybe if I labeled some of these things and told you to identify what's the deck, what's the deck, what's the purlin, what's the beam, what's the column, what's the brace? I think it's a pretty good question. All right, this is another one. This is a metal deck spanning from open web steel joist to open web steel joist. And it's hard to see, but there's a beam back here supporting these supporting these open web steel joists. So these open web steel joists are about 2 meters on center, and their depth is dependent on how long they are. Metal deck on open web steel joists and trusses. So look at this. We've got these ones are heavy duty. These look like they are not normal open web steel joists. This seems to me like there's something hefty going on. That means that this is probably an application outside the range of normal. But the deck is normal, so whatever these hefty things are look like they're still around 2 meters on center. And then it spans to another truss over here. Concrete on metal deck. Look at this. You've got that rebar, we've got our metal deck, and then they're putting the concrete on top of it. Composite deck beams. Now these are a funny thing that we don't do in Toronto very often because we're usually governed by, and in Canada really, because we're usually governed by vibration. And this is a system that allows us to reduce some of our steel. So what we're saying is we have our metal deck with concrete spanning to our purlin. Remember, a purlin is just another type of beam. So where is it? Let it come into focus here. So you can see that we have our concrete on metal deck and we have a purlin right here. What we're saying is if we put these funny little studs in, we make, let it come into focus, so if we put those funny little studs in, we make that our beam. So we take some of the deck as part of our beam. And that means the steel part can be a little bit smaller or a little bit less or a little bit lighter. So these are called shear studs, and they make the concrete and deck work compositely with the beam below. So the concrete and deck are already a composite system. So we take a composite system and attach it and make it a composite system even more. But like I said, if we can lower the steel, remember I said steel was very susceptible to vibration? Most applications, we wouldn't want to do this because then we would have to make the steel bigger for vibration, and then what was the point of doing all this? Because it actually added cost without saving us anything. This would be really good in an application where we didn't care about vibration. And remember, vibration is all about human perception, or how we feel when, now there's some extremes where we really can't have certain vibration frequencies, but that's usually not what it's about. Most of the time, it's about our perception of how the building feels. And if we can say, oh, well, this is an application where nobody cares. It's not something precious. It's not an office building. People aren't sitting here doing math all day. They're people kind of walking to and from to get something very specific. Maybe it's an industrial application. In those situations, it might be worth saying screw it to the vibration criteria and saving the money on the steel. Hollow core planks on steel. So we have our columns and we have our steel beam. Now remember I said steel beam is usually picking up deck or picking up purlins or joists, and the purlins or joists are picking up the deck. Well, hollow core replaces the deck and its joists or purlins. So now this is more like we've got a series of joists spanning in this direction. So I often think of hollow core as a series of little concrete beams with kind of a topping on it doing all the work. So this is our core. We've got a bit that's the topping, and then we've got bits that are funny little beams, and I'll show you this in just a second. Again, normally I'd be doing this on a screen for you. So you can see the red is the outline of the concrete for the hollow core. And then we've got a little bit of topping that's like the deck, and then we've got a series of concrete I-beams that are so close together they're actually touching and make one big slab. So these are spanning in this direction and being supported by the steel, which is the steel beams, which is then on the columns. Cast in place slab on steel. Not super common. We tend not to do concrete directly on steel because if we have to do formwork to hold up the concrete anyway, we might as well make it metal deck and make it composite and save ourselves some concrete and the cost of the formwork. What I like is this detail. This is a hinge. You can imagine those two things can be allowed to move independently from each other. This line right here is an expansion joint. So often we'll do this if these two buildings need to be able to move independently from each other from a structural point of view. Open web girders on metal deck. So here we've got our metal deck spanning in this direction. Now these open web girders are our joists or our purlins. So I can't tell if the child woke up or if my heat's coming on. No, it's not a child. They call them girders, but they're not our beam girders. They're kind of an alternative to trusses or open web steel joists or purlins. Now, what they do with these is they actually take a piece of steel. We have a top flange and a bottom flange. They take a solid piece of steel like that and torch it or cut it apart, lift them apart and shift them and weld them back together. Why would you do that? Well, we've been showing that the deeper something is, the longer it can span. So if we can make this deeper, maybe we can make it span longer. And I'm going to show you that mathematically next week. The depth of our element is very, very, very important. So if we can make it deeper, that's great. Now, this is rarely done. I've never seen it in Canada. In fact, I had never seen it anywhere. I had seen it touted a lot. Our market is labor cost driven. Labor is very expensive in our North American market, and materials are cheap, 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 like super cheap. So we will oversize things to save labor costs. You can imagine the extra labor involved in this versus just speccing a beam that's this deep, that's solid right there. For our market, this isn't economically feasible. Now, we're in a place in the world where things are crazy, and we were already, because we were already being driven slowly into more of a climate-based economy. So that was going to change things. We've had supply chains disrupted, all kinds of crazy things that have us at a cusp of a market that could be unlike anything we've ever seen over the next few years. So some of the things I'm telling you about what govern and don't govern cost decisions might not be true a few years from now. In the 50s and 60s, for example, our market in North America was material cost driven. So labor was very, very, very cheap, and materials were very, very, very expensive. So we would do everything we could to save on materials, even if it meant putting more man hours. I know I'm saying man, they call it man hours or person hours. I'm trying to correct all of those things that are kind of embedded weird terminology, because you know what I mean when I say person hours. I did recently see this style of construction. So Dave and I had been kind of pre-COVID doing our Masters of Tensile Fabric Structures in Germany. So we've been to Germany a few times for our program. And in the building that we were studying in, which is on the Bauhaus campus, so like the epicenter of art and design, we were in this new building that had this style of construction. Interestingly enough, it was built like in the late 90s, early 2000s, but it's in East Germany. So the side of the wall that had a really poor economy for so very, very long, and there was no jobs. So the labor hours were cheap because people wanted to work. There was a need to work. So the labor hours were cheap, but there was also still a hard time getting materials in, and so materials were expensive. So complete juxtaposition to what we had here in North America at that time, but for them in that economy at that time, it made sense to do the more labor-intensive solution as an economical means to solve their problem. So you can see, depending on where you are in the world and the time it is in the world, can have a big impact on some of these choices we make in our design process. So those are things you need to know, and they might not be things I know. There are a lot of you that are from around the world, whether it's India or China, Japan, Malaysia, Russia, and I don't know your local markets. So there are going to be things that I cannot speak to, but there are a few things that I've been exposed to at our markets that I do have some insight, and hopefully at least allows you to know the questions to ask. This is a crazy weird construction. We don't tend to add steel to concrete unless it's a retrofit. So you can see that there's concrete beams up here. So it looks like there are things in this building that were concrete to concrete. I have done projects where there were concrete buildings that they needed to add a mezzanine, for example. And so for those, we added steel into it. So this wouldn't be based on preliminary construction. This would usually be an add-on. An open web steel joist connecting to a concrete wall. So you can see there's our metal deck. Our joist comes along and it sits on a little angle that's been connected into the concrete. Gerber girder system. So this is a system where we take two beams that cantilever and drop a little piece into the center. Did I write on my... Damn it, I definitely hear a child. Okay, I'm gonna have to stop this and I'll come back to you guys in a little bit. We're close to the end anyway. Let me just see. Oh. I'm coming, buddy. Hold on. Okay, so for you guys, it's been instantaneous, but for me, it is about 2.5 hours later, and I'm soaking wet from having just come back from walking the kids to daycare and school in the rain. Okay, so Gerber girder system. It's a really cool, smart way to deal with steel. Because as much as I've been talking about weight, I haven't mentioned piece count. It's not as a driving factor, but piece count, if you have the same weight of steel in 100 pieces versus 50 pieces, so it's all the same weight, the whole building is the same weight, 50 pieces can make things cheaper than 100. Also, how you install things can be helpful. So this one doesn't reduce piece count, but it does help with installation. Okay, let me draw a full Gerber girder system here. I'll draw it not as a Gerber girder, and then I'll draw it as a Gerber girder. Okay, so the top one is 3 bays with 3 beams. Bottom one is 3 bays with 3 beams. But you see this beam cantilevers over, and this beam cantilevers over, and then we drop in this tiny little beam. What's nice is that these 2 bays can be stable, and then we just come back and drop this little tiny one in. It doesn't usually have a ton of savings in steel weight. It usually does have some savings. But the engineering is a bit complex. You have to kind of do a few different patterned load casings. To make it really efficient, and the reason it drops the weight is because of the bending moment diagrams, which we've talked about at this point. Where they become really cost effective is if you have like 30 of them, if you have 30 bays, for example, and you've reduced the tonnage just a tiny little bit, but 30 times can make a big impact in the cost of a building. We can put holes in beams. The general rule of thumb is you don't have to reinforce them if you put them in the 1/3, 1/3. So middle third of the length, middle third of the depth, and you don't need to reinforce them. Guaranteed, don't need to do it. Round holes are what we prefer. Cracks propagate from sharp corners. So this would have to be reinforced simply because it's a square or a rectangular opening. This same opening, had it been round, might not have needed reinforcing. Just some more holes in beams, even more holes in beams. Again, these are just pictures to show you what things look like. So if you're drawing something sometime, I have it's just a handy little picture guide of how things go together. Here are those Z-Girts we talked about. So this would be probably a system building, a Balin or a Butler building, and these would be the Girts on top. Architecturally exposed structural steel, and this one happens to have a casting right here in the middle as well. Actually, I believe those are castings as well. Again, architecturally exposed structural steel. This is my project, the Goldring Center. These pieces of steel here are architecturally exposed. Now, exposing steel architecturally, usually you want to do a few things to it, and you need to specify that it's architecturally exposed. And there are guidelines on what to do for different categories of architecturally exposed structural steel. One of the reasons it can be critical is we often need to fire protect our steel. Remember how I said it's non-combustible, but it's got a really crappy fire rating? So we can put something on it called intumescent paint. Now, intumescent paint is a paint that literally, when it's exposed to fire, puffs up huge and turns into insulation and protects the steel in a fire. One of the things about intumescent paint is it's very expensive, so we try to do whatever we can to limit it. Plus, it's got a bit of an orange peel texture, so it's a little bit dimply and bumpy. Some architects hate it, some don't mind it. So knowing that you've got steel exposed, and if you can have it exposed, and if not, what you need to do to it. And then for both of those, how to specify how to make it look pretty can be important. We can roll steel. We have presses that can roll it. The bend radius is dependent on the depth of the element. The deeper it is, the harder it is to bend. That's one of the reasons why glulam is kind of great in wood, and we'll talk about that in a few weeks, and I'll show you an example. Here are just some steel details. This is a pretty typical detail right here. Here's a pretty typical plate. So this would be a brace coming off over here, connected in. This beam here is dropped because these open web steel joists have a joist shoe. Normally we keep the top of our steel flush, even if they're connecting into each other. We would cope the top of the end of the steel so that they can fit together. This one needs to be coped and raised up because it needs to be at the same datum as the open web steel joists, because they're all picking up the same piece of deck. Just a weird thing, just to show you that you can build up weird elements. This would be expensive and unusual now. This might have been done back in the day before they had rolled HSSs. Here are some really long span steel joists being installed, and I'm not calling them trusses simply because they're at 2 meters on center, but they are custom. They're not your typical open web steel joists. These ones were designed for very long spans, but you can see that they're at a really close spacing. Here are some long span trusses. Now these are monsters. Look at how deep they are. These would often, when they're this big, come in pieces and be brought together and then bolted. Welding in the shop, bolting in the field. Those are things we try to ensure. We like to make sure that we do all of our welding in the shop and bolting on site. Here you can actually see one of those splices. So you can see that they had ends of parts of the trusses that need to come together, and they put plates and brought them together, and then they bolt them together down the middle. One of the great things about steel is you can have really tight tolerances because they can actually even lay it out in the shop and ensure they have the right fit up. Just some cool steel trusses to show that you can do neat things with your trusses to meet your profile. So if you've got, you know, shape to your roof or shape to your soffit, you have options on what you can do there. You can have two-way trusses if you want, which essentially means, or I guess three-way trusses, would be a space frame. So you have not just a linear kind of shape like this, but also going in the other direction as well. Here's curved steel again. You can see that they've rolled this steel. Here is another way to protect steel. So I said intumescent paint is what we do when it's exposed. You can spray on fireproofing. If you've ever been in kind of some of the new parking garages that have steel columns in them, rather than the old concrete ones, they will have sprayed it with fireproofing. One of the weird things about the fireproofing is it's also a sound insulator. And I was in one a couple years ago when I got out of the car, and it was surreal. It sounded like I was underwater almost because the sound was so dead. It's what I would imagine being like in a sound booth might sound like. Sound didn't carry at all. It was instantly absorbed. Again, once you know you're working with steel and there's a budget, you can do very intricate shapes. Again, tolerances can be very tight because we can do so much fit up in the shop. We've got curved two-way curved beam action. Here's a column that goes, this one is multiple stories, and then this one is multiple stories. So as much as we might think of columns as discrete segments going up the building, we might do them in multiple lifts. So this is a two-story lift of a column. So even though this is one story and this is one story, they brought it as one piece here. And you can see the transition that as the column goes down the building, it's taking on more and more load. At the roof, it's just supporting the roof. At the, I don't know, let's say 10th story, it's supporting the roof and the 10th story floor. So from 9 to 10, it's got more load on it. And that continues all the way down to the ground. So our axial loads on our columns increase. If you guys remember that axial force diagram for column I put on last week, or maybe it was the week before assignment, you could see that it increased as it went down the building. We can end up with quite large columns as we get down towards the bottom. Here is a neat column. So this column has gravity load on it, but it's on the outside edge of the building, and wind is blowing on the building. These are spanning from column to column to column, and they're called wind girts. And they are acting in a similar way to a roof joist acting on a beam. So these are collecting wind and pushing on the column. So our column is also acting like a bending member. So if I have my trusty foam block, I've got compressive load, but I also have wind bending on my column. Here is just an industrial building with some crane columns. Again, these are just, I don't have a lot to say about some of these images. I just want to show you that they exist. So maybe sometime later in your career, if you're looking for something, you can come back and maybe see these images. These columns are neat. So look at this. They change their profile. Next week, we're going to talk about what depth means to moment. So if this is in bending, let's turn it this way. If this is in bending, we're going to talk about, well, actually, here's a good example. I'm bending this. I'm trying to bend this with the same amount of force. It's a lot harder to bend it when it's deeper. Intuitively, you know that. It's one of those things you intuitively know. And next week, I'm going to show you the math to prove that. Now, this wind column is bending like this. Do you guys remember, for a simply supported spanning element with a continuous load on it, where was the moment the highest? Yeah, the moment was the highest right at the middle. So if we needed the most moment resistance at the middle, and depth helps us deal with moment, well, look at this. It's the deepest right at the middle of the column, and then it tapers top and bottom. Massive built up plates, a Mies kind of special. Again, just to show you that this was a built up column. We already looked at this earlier. I can't even remember how many slides I have in this. A cruciform section, a really popular kind of style of column in the 50s, 60s. So when we do a cruciform column, again, it's built up. We don't do it as 4 pieces of steel. We would do it as 3 pieces of steel, where 1 is continuous and 2 butt up against it, and then we'd weld all of those up. I'm gonna sneeze, sorry. Oh, excuse me. Some architecturally exposed columns. You can see that they've added these flanges on what look to be round HSSs to help increase bending capacity. So you can start to do really fancy things while still meeting the structural intent, or even not meeting it, even following its demands. You can actually turn columns into trusses if you need to. Here are some really cool truss columns. These are 3-dimensional ones. They have 3 posts coming down. Here they've taken the time to detail true pinned connections. Cable stayed columns. So if we have columns that go up with nothing to brace the top of it, we need something to brace it, so we'll put cable stays in. Masts are essentially what we would call a column coming up out of the top of a bridge that has then stays that support the bridge. So those would be called masts. Masts that have been cable stayed. A truss mast. So at the center of a tent, you can see that again, it's a 3-dimensional truss column with a pinned base so that it's not attracting moment. So what do the bases of things look like? This is a pretty typical column base. This would be pretty standard. Now, I can tell you that on site, if there is something that is done wrong, it's these anchors being cast in the right spot. That is probably 60% of problems that I deal with on site, is that the anchors aren't in the right spot. So trying to give tolerance or being very specific of the importance of that is huge. It tends to fall through the cracks because we have the steel supplier creating the anchor bolts and the concrete contractor installing them. And the concrete contractor doesn't necessarily, is not necessarily aware of the importance of that element that is crucial to the steel fabricator. So having a contractor that can really mesh those two trades is really kind of a real bonus on a project. Here's a really heavy column base. Look at the thickness of that piece of steel. It's massive. You can imagine the loads coming down. We want to spread it out over a bigger area. If we have a load over a bigger area, we reduce the stress or the pressure on the underside of that base plate, meaning that's what stops us from failing the concrete. A really cool kind of heavy-duty base of something. I don't even know what it is, but look at all of these gussets. There's the base plate. Those are the anchors for it. And then we've got massive braces coming off of it. This looks like something very industrial, a plant of some sort. So this column, for whatever reason, wants to lift up out of the ground. These anchors go down deep into the concrete so that if that column tries to lift up, it has to bring all of the concrete with it. And that is actually a surprisingly difficult detail to create. There are lots of ways to do it. Everybody hates doing it. They hate building it. Architects hate seeing it. Engineers hate designing it. But it happens at the ends of brace frames, at the back spans of cantilever beams. You can have it due to cables in projects. So it is a condition that we have to deal with, usually in lighter projects that have lots of lateral load. Here's one that's resisting moment. So remember, if something's trying to tip over, we can try to fix the base of it so it's a little bit harder to tip over. If you were standing up and someone tried to push you over, the thing you do to stop from pushing you over is widening your feet just a little bit. It's harder to tip over. That's essentially what we're doing here. To deal with a moment-resisting base, we widen the connection. So the farther these anchors are apart, the better at resisting the moment. But now we have the problem that the moment has to transfer from the column into the base plate. And if this is the size of the thing to resist the moment in the member, we've just got this itty-bitty little thing here to try to resist the moment. So it's a balancing act. The further apart, the better for the anchors, but the further apart, the worse for the base plate. So there is a combination there, and that's why often sometimes you'll see gussets. Here's them milling a column base. Look at that. Look at that crazy cruciform section. Look at the built up steel in that. It's wild. All right, an arch. Now, we aren't going to spend a lot of time talking about unique structures like arches and suspension, but if we resist that bending and turn it into axial forces at the end points, we're pushing down, but it wants to splay out. So yes, we have our gravity load that we have to resist, but now we have to deal with that thrust force. That's why bridges with arches often have a big buttress right here. Suspension bridge is the same thing, but inverted. So instead of a thrust, there's a pulling force. So there's a compression load down, but also a pulling force on those supports. diagonal tension and compression brace. So we can have braces that work in tension or in tension and compression, or we can have ones that only work in tension. But if we have wind going back and forth, if we have one that works in tension and compression, we only need one member no matter what. If we have something that can only resist tension, then we need a brace to resist the load in that direction, and then we need a brace to resist the load in that direction. So I can tell that this is a tension compression brace because they're going in the same direction and there's only one in that direction, so they must be resisting compression. Here's some details of what a base might look like. I've shown you some others already. Here's a tension compression brace coming in to a column and a beam. Here are tension only braces. You can see we have them going in opposite directions. So these would often, and they're very slender for how long they are, which means they don't work in compression. Remember, if you try to squash something in compression, it has this weird tendency to want to move sideways. And we're going to talk a lot about that next week, but I think intuitively you understand that. If you take an elastic, you can stretch it and it can resist load, but you can't drop that weight on top of it. It tries to buckle. A really slender brace element is only going to work in tension. So then you need one to resist the load in the opposite direction. You can offset them. So you can see there it's offset. X-bracing with angles, these would be tension only. X-bracing with channels, again, they'd be tension only. Rods, definitely tension only. This is usually actually decorative. Sometimes it might be used as the actual lateral system simply because this detailing is so difficult. Now, they have so many of them that the force in each system is only a fraction of the whole of the building, so maybe they were able to solve it with some unique detailing. So you can see here's the detail at the base, and here's the detail at the midpoint where they intersect. Here's a massive water tower with X-bracing in between the columns. You can get fancy in your diagonal bracing. I know Dave and his team are doing the academic wood tower that's perched over Goldring Center right now, and there is unique bracing patterns in that building. You can do K or chevron bracing. I know you would think it would look like a K. Those do exist as well. Double chevron, K or V bracing. You can do super bracing. So this element and this element work for that floor, and this element and this element work for that floor, but they change their location going up the building. And never forget your detailing. I have found that these gussets with certain fabricators end up being very large. They don't always need to be. But the work that went into building this by having this welded here, these elements welded here, they could have just put a plate in there for its entirety. Probably would have saved a lot of work had they seen the shop drawings for this element. You can incorporate steel and wood together to create interesting details. Now this will show up again in the wood lecture, obviously. An eccentric bracing joint. Now this right here is likely part of seismic design. Now one thing they do specify that if you are doing capacity design, which is again that system where you absorb energy in your joints of your building to help limit the earthquake loads on your building, they need to be spray painted with orange paint so that if somebody comes in later to do demolition or reconstruction or make changes in the building, it is a big flashing light that, hey, this was the lateral load resisting system and it's an important part, don't muck it up. Bracing on a round building. Here's some architecturally exposed bracing. You know, Dave and I always joke around that you can take your paint all at once or spread it out in little bits. It's like ripping off a Band-Aid or doing it slowly. It hurts less, but it hurts longer. You can have one big brace located in one or two spots, or you can have lots of little braces spread out all over the place. And then there's a varying range in between there. Here's a cool combo system. My pals at Cast Connects designed the casting here. Blackwell's office is actually in this building. It's a really cool building. It's 134 Peter. If you get a chance to kind of walk down there, it's a neat thing. These are the lateral load resisting systems of the building, because what this is an 11-story concrete building perched over a 4-story heritage building. Here is a system building. This one's a 3-pin arch, so there's a pin here, a pin at the ground here, and a pin on the ground on the other end. And you have 2 frames leaning against each other. They can't tip that way because this one would have to fail, and they can't tip this way because this one would have to fail. So it's a stable system, and they can usually end up being quite refined elements if you accept that you're going to see a lot of that kind of refinement. A steel moment frame. A moment frame gets rid of bracing. Now, I know we're seeing bracing here, but that's temporary bracing for construction because there's no diaphragm on this building yet. Moment frames. Moment frames are bigger and heavier, and they deflect more. Yes, you can use them, but you are going to be surprised by how big the members are, how heavy the members are, and how much they deflect. So I will, in the last lecture, show you a comparison between a steel braced frame and a steel moment frame to kind of show what the cost implications are. Here's just a small steel moment frame. We always talk about the Toronto Special, which is a townhouse. So they're usually long and very narrow. And at the back, they always want to bust out the back wall and make it a sunlit kitchen in the back. But now they've taken out their lateral load resisting system. And so we often have to come in and put this steel braced frame in. Okay, that was just a bunch of pretty pictures to show you as a resource. This wasn't supposed to be a lecture on how to build steel buildings. It was a hole that I saw in the curriculum that I thought you guys might benefit from. So I really wanted to show you those pictures. You should know hot rolled versus cold rolled. What's the nomenclature of a section mean? And you should be able to look things up on those charts that I gave you. I will be very specific if I'm talking about the nominal mass or the theoretical mass so that you can pull that information off. You should, again, and we talked about this last week, know what the steel stress strain curve looks like. You should know the basic steel properties, or you should be able to look at that list of basic steel properties that I gave you. Steel advantages and disadvantages and its uses. Wonderful exam questions and assignment and quiz questions, because it's just a list. You just have to look it up. Definitely know your steel sizing guidelines or rules of thumb. You should be able to look at a plan, look at how long a member is, and tell me how deep it should be, but not just how deep it should be, an available size of depth that it should be. If I give you the depth of a member, you should be able to tell me how long that member can be. Remember, it is the reverse, so then it's the depth times the sizing guideline to find the length. And you should just have a general idea of some basic steel construction images. Maybe the one that I said would be a really good question, like the first one. Okay guys, next week there is a lot of info, but surprisingly little of it do you have to memorize or do work with. There's a lot of data I have to tell you so that I can tell you the stuff you have to know. So it's going to sound really overwhelming next week and really intense, but you will see that the work I require from you out of that lecture is not that difficult. So it's more of a, I want you to hear the process and I want you to understand where everything comes from so that then you can do it the easy way. So I'm going to tell you the hard way so that I can show you the easy way, and then you will do the easy way next week. Okay, Have a great week, everyone.